In our previous sessions, we had learned about the general linear model for longitudinal data. The general linear model for longitudinal data is an effective technique to model the longitudinal data. In the coming few sessions, we would be talking about something called the linear mixed model. So, linear mixed model is another technique of modeling longitudinal data. In this specific session, we would be talking about what motivates us to use linear mixed models. Now, to do that, we would be using the Orthodont data set. Remember that the Orthodont data set is in the NLME package in R, and while we would be using this, we won't be using the entire data set. Rather, we would take a subset of the data, that is the subset of measurements only for the boys. We would start with three approaches. The first approach would include individual modeling of each boy, that is, we have 16 boys. So, basically we would be fitting 16 linear models or 16 simple regression models. Then we would advance into a single model, but this time we would include a fixed effect parameter for each of the boys. Finally, we would take that to the linear mixed modeling strategy. While doing so, we would be seeing the pros and cons of each of the modeling strategy. So, the data set that we would be talking of is the Orthodont data set. It is the data set by Pathoff and Roy, and this data set we have used it while we were doing exploratory data analysis for longitudinal data. So, the data set is on 27 children, 16 of them are boys and 11 were girls. For each of the subjects or each of the children, here the subjects are the children, the distance from the center of the pituitary to the pterygomaxillary fissure was measured in millimeters, and this measurement was taken at 4 ages, at age 8, at age 10, at age 12 and at age 14. The data is packed as an object in the R package NLME, and it is called the Orthodont object. However, to get the motivation about linear mixed model, we would be dealing with a subset of the data, that is the Orthodont data only for the males or the boys, and interest is in modeling the individual growth curves of the boys. Here, instead of taking age as the regression parameter, we would be taking a age shifted by the mean. The mean comes out to be 11 years. So, we would be taking age minus 11 instead of age in the regression equation. So, to load in the data, we should call first library NLME, which loads the library in R, and then we would use the subset command, which is subset Orthodont, that is Orthodont is the data, and we want to make a subset based on sex, which is specified as males. So, what it does is it selects all the data for which sex is male, and we have stored it in another object called orthomale. Now, if we just plot orthomale and y lab equal to distance, so we specify what is the y lab, that is the y label. So, what it plots is the individual profile of each of the 16 boys, and we can see from here that there is a quite lot of individual variation between the boys. As an example, we can take M11, so the male 11 versus male 13. So, we can see here there is a lot of variation, or maybe say male 7 versus male 9 or male 15 or male 1. So, internally there is a lot of variation among the growth trajectories of the individual subjects, the subjects here being boys. So, the analysis strategy that we can take is we fit a linear model for each individual, meaning if yij is the response variable, here the distance ij. So, I signifies the subject, j signifies the time point, I is here 1 to 16, j is here 1 to 4, and we fit a linear model or a simple regression which is like beta naught I plus beta 1 I Tij plus epsilon ij. So, what are these quantities? Beta naught I is the individual intercept for the ith subject or the ith male or the ith boy, and beta 1 I is the individual slope for the ith subject. Tij is the time at which it is measured. Note that here Tij is equal to Tj because all the subjects are measured at same time point, and epsilon ij is the random error associated. We can fit this model very easily using the LM list function. So, what we would specify is LM list distance tilde means explained by age minus 11, and I age minus 11 means to treat age minus 11 as one variable. So, what it does is it creates a new variable which is called age minus 11 and subtracts 11 from all ages and specify the data equal to ortho. Note that this is equivalent to fitting 16 regressions, one for each subject. There is no point in specifying the 16 slopes and 16 intercepts, but we have a intervals function which produces the confidence interval, and we can use a plot function to see what's the confidence interval looks like. And the moment we use plot intervals lm.list, so lm.list is the object we created where the lm list objects or the 16 regression equations are stored. It gives me the intercept and the slope for each of the 16 males. Now, what do we find here? We find that there is quite some variation in the intercept. So, here it starts from here. So, the median intercept or the estimated value is here, and it goes up to this point, and while for the slope there is not much of a variation. So, it is more or less around a specific line. Now, what are the problems of this analysis? First of all, this analysis is intuitively very sound in the sense that for each of the individuals we are performing one regression. So, that means if we have n individuals, we perform n regressions and report them. But it does not specify what is the overall pattern. So, that is one of the major concerns here. So, we need to know what is the mean trajectory of the population. Unfortunately, such an approach does not give us what is the mean trajectory. The plot, as we had already seen, shows that there is individual level variation in terms of both intercept and slightly for slope also. But there is no quantification. We can still produce naive estimates. How? We have all the 16 intercepts, we can take the standard deviation of the 16 intercepts, and we have the 16 slopes, we can take the standard deviation of the slopes. On doing that, not the R code is not shown here, but that can be done pretty easily. We see that the value comes out to be, for the intercept it comes out, the standard deviation comes out to be 1.83, while for the slopes the standard deviation comes out to be 0.41. Note something, here we are fitting 16 regressions and here only time is the covariate. So, we have one intercept and one slope for each of the 16 subjects. So, this results in 32 regression estimates, 32 beta naughts, 16 beta naughts and 16 beta 1s. Plus, for all this 32, we have the same number of standard errors as well as one variance parameter of the random error. So, that means we are calculating so many parameters. Ignoring the variance parameter also, we are calculating at least 32 regression parameters for unbalanced design. Now what happens here, the situation is in our favor in the sense that for each of the individuals we have an equal number of observations. What if each of the individuals had an unequal number of observations? There, for further analysis, we need to weight the precision by the precision of the parameters, or so that creates a problem. Another strategy that might be implemented and which is better than the individual regression strategy is to have a general intercept and slope for the data and include an indicator variable for each subject in the regression, or in other words, we have one slope but 16 intercepts, and all the 16 intercepts are fixed. So that means for each individual, so individual I have the intercept beta naught I, while all the individuals have the slope beta 1. Here note that the slope is free from I or the subjects, whereas the intercept contains the subject index. So the model becomes Yij is equal to beta naught I plus beta 1 Itij plus epsilon ij. So beta naught I and beta 1 are the individual intercepts and slope at the population level. So beta naught I is the individual intercept, while beta 1 is the slope at the population level. This model can be very easily fixed using the command LM. So we all know LM stands for the linear model command, and so LM is distance explained by subject. Note the use of the factor subjects, and I have given -1 to have a different representation, otherwise it would have given, so -1 means without intercept. If I had added the intercept, then what would have happened is it would have given the mean effect and the deviation of each subject from the mean. We don't want that at this point of time. So I have written the model as distance explained by subject plus I age minus 11 without the intercept, that's -1, and the data is orthomel. Summary ortho.lm would produce a lot of things, but just to visualize this we can use another excellent package called the effects. So if I just load the package effects, library effects, and then there is a function called all effects. So all effects of the linear model object. CEX is just this magnification size, and ROTX is how the axis labels are printed, so it's rotated by 90 degree. But that's not the issue. The issue is that here what we get is we get 17 parameters. There is 16 parameters for the intercept because there are 16 subjects here, and here we are, so the plot here shows the confidence interval of the 16 parameters for each of the subjects, and here is the effect of age. So which, because it's a linear model, so we get a straight line, so we have one slope effect and 16 intercept effect. So what is the problem here? The problem here is that although we have reduced the number of parameters from 32 to 17 excluding standard error and the variance parameter, but still 17 is quite a high number. Also there is a significant improvement in the precision of the slope parameter, which is 0.093. So this can be obtained using the summary function. It's not printed here, but if you print the summary function you would see that the standard error comes out to be 0.093, which is much better as compared to 0.41. So this is significant reduction. And if you see the values of the individual intercept from the first model and this model, then they are similar. Finally, we go to the third model called the mixed effects model. Now in mixed effects model, what we do is we fit a general intercept and slope for overall data, but there is deviations for each subject from the general intercept. We assume that the deviations are random in nature and we add a random effect. So basically we can say that Yij is equal to beta naught plus Bi, where beta naught is the intercept of the population or the general intercept. Bi is a subject specific random effect for the ith subject, and B1 Tij is the slope associated with the population level. Epsilon ij is the random error. And note that here both beta naught and beta 1 are free from I, indicating that they are independent of the subject. But we have a factor called Bi, which is nothing but a random sample from a normal distribution having 0 mean and variance sigma square b. Now, what this Bi does is it induces the randomness or the subject specific effect present in the data. Another thing that we assume is that Bi and the random errors are independent. So, how do we fit the model? Now we come to the function called LME, and the LME function is in the NLME package. Since I have already called the NLME package, I am not including it. So, again it gives LME is distance explained by I age minus 11, random equal to 1 given subject, data is equal to orthomale. So, here we are getting, so this looks very similar to the LM command, but we have an extra object called the random, and here what I am specifying is random is explained by 1 given subject. That means 1 stands for the intercept. So, I have a random effect for each subject, and the data is orthomale, so the data that needs to be used. I can use summary ortho.lmes, and that would give me a lot of output. So, I haven't printed here that, but I would urge people or you people to do this. And then I have introduced another command called the intervals. Now, previously we had used intervals of LM list, but here we are introducing intervals of LME object. So, intervals ortho.lme. Again, this would give a lot of outputs, but the basic thing that it would provide is provided here. So, we see that here are basically 4 parameters: beta naught, beta 1, sigma b and sigma epsilon, and these are the confidence intervals for each of the estimates. So, we started with 32 parameters, reduced it to 17 parameters, and now we have only 2 parameters which is addressing the mean model, and one random effect parameter called the sigma square b, and one variance parameter for the random error, which is sigma square epsilon. That is a typo here. So, sigma square epsilon is all that is needed to explain the model. And what we also observe is that the parameter estimate of the slopes are similar for the fixed effects model. However, if we see the standard error for the slope of the parameter intercept, then it has reduced for random effects model as compared to the fixed effects model. How to see the parameters? The summary function of the fixed effects model and the summary function of the LME would provide the random effects model. So, now this gives us a strong motivation of why to use linear mixed model for longitudinal data. The first motivation is that we start with a lot of parameters, and using linear mixed model for longitudinal data, we can reduce the number of parameters. That's motivation 1. Motivation 2 is that linear mixed model has a nice explanation. So, what it does is it says that you have a general model or a mean model at the population level, and the randomness and the correlation is introduced both the randomness and the correlation is introduced by the random effects. So, in the next session we would learn more about the theoretical aspects of random effects. In this session we have learned what motivates us to use linear mixed model in the context of longitudinal data. So, we started with fitting individual regressions to each of the subjects, and then we extended the idea by fitting a fixed subject specific effect, and then again further extended the model by now introducing a random effect for the subjects. While doing so, we also learned few of the R functions which performs this sort of modeling. Practically speaking, the linear mixed model can be completely done by the package called NLME. In the next session, we would be talking about the theoretical aspects of linear mixed model. But then we would be doing a complete analysis where we would be extensively using the functions of the NLME package to fit the models.